Welcome to everybody. Thank you for attending. So this is the title of my presentation. I'm not going to repeat it. And I should pass very fast on this slide because the important thing is to show you the contribution by many people, PhD students, postdoc, colleagues, some of them being three of them in the row. And I should go very fast because I don't want the one who is missing, and there is probably one missing, to find out. So let's continue. So let's go with a general introduction. I am very sorry to tell you that, well, we are speaking about something that is cheap and easy. Marine magnetic is a cheap and easy technique. To proceed, you only need a marine magnetometer, a cable, and a little bit more importantly, a ship. If you have that, you can collect data everywhere in the world on the sea, and you can do discoveries of importance, like those people did in the 60s. They found the marine magnetic anomalies on the seafloor. Those are two famous examples, of course, that everybody knows. And to create that, of course, you need two processes. You need geomagnetic polarity reversals and other geomagnetic fluctuations, possibly. And you need plate tectonics, and more specifically, seafloor spreading. Okay, we know that for almost 60 years, since the famous paper by Vine and Matthews in 1963. As a result, marine magnetics represent an invaluable tool to determine the age, structure, and the evolution of oceanic basins. And this can be done at local scale. Here is an example from the central Indian ridge at 19 degrees south. You see the magnetic anomalies, the peaking, the interpretation of the polarity boundaries. Then we get the edges of the lithosphere draped on the bathymetry, and the plate reconstruction showing the evolution of the area. This can be done also at more regional scale. Here's an example from the central Indian basin, where you see interpretation of marine magnetic anomalies in the very nice anomalies in this area, comparison with the model computed from the polarity time scale, and the fitting of the model and the anomalies, which gives the age of the lithosphere in the area. It can be done also at the global scale, and I have to show you this very nice plot of the evolution. You see the big jump between 120 and 83 million years. This is the evolution of the Earth's continents and oceans for the last 160 million years. That is mostly obtained from marine magnetic anomalies. Okay, so this is conventional marine magnetics. It relies on a model, the alternance of normal and reverse polarity intervals, and a magnetized layer that is about half to 1 kilometer thick, that correspond mostly to the extrusive basalt layer. The method is, as you could see just before, recognize the sequences of anomalies by comparison to model, and date the seafloor, build isochrones and decipher the basin structure, and therefore subsequently adjust the conjugate isochrones and reconstruct the basin evolution. Beyond this conventional approach, the marine magnetic anomalies also contain information on two major aspects of interest. First, they tell us something about the geomagnetic signal carried by the anomalies. That is the evolution of the field in the time, the history of the geomagnetic field created by the Earth's core for the last 160 million years. That's what I call the geomagnetic signal. And second, a lot of information also on the recorders, that is the oceanic lithosphere that carries that signal. So the structure of my talk will be in three parts of very different lengths. The longer part A will be trying to go toward a consistent magnetic picture of the oceanic lithosphere. The second part will deal on the advantages to master both the signal and recorder properties to better interpret anomalies in complex basins. And the part C will advocate the need to collect new, well-navigated magnetic data to increase the resolution of plate reconstructions. So let's start with the part A, toward a consistent magnetic picture of the oceanic lithosphere. Well, the conventional model, as I just said before, consider a simple source, as it is here on the right on the 1966 paper, considering only the extrusive basalt layer made of block of alternating polarities. Some previous observation, however, suggests that the source of seafloor spreading anomalies is not limited to the extrusive basaltic layer, and that gabbro and serpentinized peridotite may also contribute to the anomalies. They include these three things that I will rapidly describe. First, the amplitude of satellite magnetic anomalies. Here in the top is a satellite magnetic anomaly at 400 kilometers from MaxSat and some other satellites. You see that, we selected this area because the anomaly are east-west and they are better acquired by north-south flying satellites, but there are other areas that show the same kind of thing. You see that the anomalies in this area, the long wavelength anomalies in this area, are parallel to the Pacific Antarctic ridge and to the isochrone of seafloor spreading, showing a high on the ridge, lows on both sides, and a high again close to the Cretaceous quiet zone. Okay, we can model those anomalies just assuming, making a model, assuming the age of the lithospheres, the rotation and paleomagnetic poles for all the plates, and the magnetization model for vertical section. This is what you see here, and we are able to model those anomalies in a reasonable way. But well, one important result from that is that seafloor spreading anomalies are also observed at the altitude of 400 kilometers high, which is not very well known. And one of the problems is you have to put a strong magnetization. If you assume only the basaltic layer of 1 kilometer, you have to assume magnetizations as high as 20 ampere per meter to fit the model and the observations, which is much too high for all the oceanic basalt, which would be okay for ridge axis basalt. And so if it cannot be the basalt, it means that we have deeper sources, and this model was actually computed with deeper sources. A second observation comes from the anomalous skewness of marine magnetic anomalies. That is, the shape of the anomaly is not exactly fitting the model, but is more consistent with something that is slanted in depth. And this could be either the field that is showing some asymmetry during the evolution of a reversal period, polarity period, or it could be just something related to the source. And we observed that actually there is a relationship between the spreading rate and the anomalous skewness. The anomalous skewness is high for slow spreading rate and almost disappear for very fast spreading rate, higher than 50 kilometers per million year half rate. So this means that it is related to the spreading rate, then to the source, then to the lithosphere. And so for fast spreading rate, we have almost a classical block model. And when we decrease the spreading rate, we have deeper sources that start to create some signal and contribute to the magnetic anomaly. A last but very important observation comes from the rocks themselves. The magnetic properties measured on the dredge and drilled oceanic rock sample shows that gabbros and serpentinite bear a significant magnetization. And a very important observation here is that the basalt have a much stronger magnetization, okay, but they are thin. And they have titanomagnetite as the main barrier that is showing current temperature between 100 and 300 degrees. Conversely, the deeper layer are much lower magnetization, except possibly the serpentinized mantle, but in some cases only. They have magnetite, and the magnetite resists much more to increase of temperature, as we will see later. So we investigate marine magnetic anomaly in specific environments to obtain independent and complementary observations on the magnetic structure and properties of the lithosphere. This observation confirms that the source of seafloor spreading magnetic anomaly is not limited to the extrusive basaltic layer. And I will discuss about oceanic core complexes, subduction zone, passive margin, post-rift, and sun-rift sedimentation. Of course, I will be very brief on those topics because for the interest of time. First, the detachment. Here is the famous detachment at 30°20' north on the Atlantic that has been surveyed by Cruz Odemar, led by Ramirez-Cartin. And this is the result of the inversion of the marine magnetics that were collected by the German AUV Abyss in the area. What you can see is you have a very strong magnetic anomaly that is observed here between a positive and a stronger and a lesser magnetization, to be clear. And this anomaly cannot be the Bruns-Matuyama because it is much too closer to the ridge axis. It cannot be related to intensity variation because intensity variation would not be that strong. And it's more probably a petrological boundary between an area with magnetized gabbro and an older area which was only serpentinized peridotite with lower magnetization. On the southwest Indian Ridge, our recent results show that the surface detachment, when they are made mostly of serpentinite, they show very low magnetic anomaly compared to the magnetic anomaly on the same period, the Bruns period, the anomaly 1. On this area, you have the breakaway, so you have basalt, and this basalt is more strongly magnetized. Here we have Jaramillo, and we see very nicely the reversals on this basaltic area. So that means that when we have serpentinite, you usually have a very low or non-existent magnetic anomaly. And when we have gabbro bodies, those gabbro bodies are causing some magnetic anomalies. And what is definitely controlling what happens, what is observed, is the degree of magmatism. And here on this paper that was just published, we show that actually you can model pretty well the magnetic anomaly on sea surface data by varying the degree of magmatism and by considering gabbro bodies as a secondary source of a magnetic anomaly on the detachment surface. This is confirmed by our observation on the Carlsberg Ridge. Here you see a very nice detachment surface at the axis of the Carlsberg Ridge. This was a cruise Carlsmag led by Nicolas Chamouk. And if you look at the magnetic anomaly, even all those detachment surfaces, they show very nice magnetic anomaly. So the interpretation for that is it is magmatic, and most probably we have gabbro bodies that are explaining those magnetic anomalies in this area. It should be observed in this area that if you look at the actual anomaly here, it is right over the ridge axis, the axial valley for the place where we have a standard symmetrical accretion, but it is displaced to the detachment surface on this area. And so the offset between these at this secondary non-transform discontinuity is quite different if you consider the axial valley or if you consider the magnetic anomalies. This is something to consider also when we do plate reconstructions. Let's go to subduction zone, and this is the work that Anjinche has done during his PhD. Actually, in this area, we see, this is off Japan, here is a Japan trench, and this area show magnetic anomalies that are nicely fading away thanks to the huge amount of data that were collected by our Japanese colleagues in the area of their coast. Incidentally, I should mention that it is also the area where there was a Tohoku earthquake 11 years ago. These anomalies are progressively decreasing, and this is due to several effects. First, because of the subduction, the anomaly, the slab is getting further away from the observation, so the anomaly is decreasing. But we can correct this effect, of course, and we see that the decrease after the trench is quite rapid at the beginning, and then that does not decrease so much after that. And we interpret this as reflecting the demagnetization of the extrusive basalt, where the titanomagnetite is not very strong because of the to the temperature. It is removed quite easily by a modest heating of a couple of 100 degrees. And the magnetite after that is, of course, stronger and require an additional burst of temperature to disappear. And if it is correct, this interpretation means that about 40% of the magnetization is carried by the deeper layer, when about 60% is built by the extrusive layer. Also, it should be observed that we have a decrease of magnetization even before subduction, and this is due actually to the fact that the outer rise is rejuvenating normal faults and start an hydrothermal circulation that is also altering by about 20% the lithosphere in this area. Okay, now let's go to the margins. With Roy Granot, we have shown that magnetic anomalies in the South Atlantic between South Africa and Argentina mostly, they have been created at the same area, and when we reconstruct them, we can see that their signature is very different. Those on South America are very smooth, very low amplitude, and those on Africa are much stronger. And the major difference between the two areas is the amount of sediment. There is not so many sediment, maybe 2 or 3 kilometers in the African side, and they are up to 7, 8, 9 kilometers of sediment on the American flank, and it makes a difference. And actually, our interpretation, I make the story short, but we did models to give substance to this hypothesis, is that we are heating the lithosphere, of course, and the crust, and the part on the South America has been heated more, and the titanomagnetite has been mostly removed, erased. The magnetization has been erased on the South American flank. But on Africa, we have much less sediment, so it was not hot enough, and we keep a significant part of the titanomagnetite of the extrusive basalt. Now, if we go deeper, this is a very interesting area in terms of early accretion of oceanic basin. This is the Andaman Sea. The Andaman Sea is located between India, there are Andaman Islands which belong to India, and Myanmar on the other side. And it is a very strange spreading area. You can see the earthquake are telling us that all this plate boundary is active. And we see some things that look like abyssal hills and an actual valley on the west, and some things that look more like a graben filled by sediments on the east. All of it active. And if we look, well, this is a seismic expression that confirms what I was just saying. And if we look at the magnetic anomaly, well, on the west, we see a magnetic anomaly that resemble and can be interpreted as seafloor spreading. But on the east, we see almost no magnetic anomaly. Actually, if we look more carefully, we see some kind of long wavelength anomaly that correspond to the whole oceanic basin of the area. And this is something that deserves to be explained. Actually, when we go to another area, that is the Red Sea, here are some data that were collected quite a long time ago as part of the Saudi-Sudanese Commission for the Red Sea. And those anomalies, those data are showing very nice high amplitude, short wavelength anomaly near the axis that are well known and have been interpreted as an actual anomaly and anomaly 2A. They are just normal, as we say, but there are also those anomalies that are more elusive, longer wavelengths, smaller amplitudes on the side that can be followed along the axis for quite a long, on a long distance. Those anomalies have sometimes been interpreted as dikes, but dikes has no reason to be symmetrical with respect to the spreading center, and they have no reason to be so consistent over long distances. So what can they be? Well, they don't model very well with classic magnetic anomaly modeling. We do not recognize them. Some people have tried some stop and go model trying to find all the anomalies, but in this case, why would spreading restart exactly in the place where it stopped before, instead of just moving and changing and breaking the oceanic crust that is as it is seen in other places? Well, our suggestion was we made models. We use actually exactly the same model we used to explain the skewness in the previous slide, but we removed the extrusive basalt. And if we do that, we have 4 different models that are more or less similar, but with slightly different hypotheses. And these models are fitting the observed anomaly pretty well. You have this anomaly that is this one, you have this one that is this one that is this one. And this is quite correct on both sides. So what does it mean? It means that we don't have layer 2A. And this is the same in the Andaman Basin. We don't have the layer 2As that create the short wavelength anomaly, but instead we have only the deeper sources, the gabbros, the peridotites, eventually seals that create those long wavelength magnetic anomalies. Why do we have that? Well, in the case of the Andaman Sea, we have a lot of sediments, and sediment comes faster than seafloor spreading can create a basaltic layer 2A. So the basaltic layer 2A does not happen because sediments are smothering it. Same for the Red Sea. In the Red Sea, you have a thick salt layer, and that salt layer, salt is deforming when you have extension. So the salt layer is never broken, and the basalt never go to the surface. So you don't create the extrusive basalt layer. You have only intrusive basalts, gabbros, serpentinized peridotite, if you can have water going that deep, and that creates those longer wavelength magnetic anomalies. A similar thing is observed in the Gulf of Mexico, as you can see in a recent work that we did with Andrina Garcia Reyes, appeared in the EPSL this year. You see that the Gulf of Mexico shows long wavelength anomalies here, and it does not show short wavelength anomaly anywhere. And those long wavelength anomaly can be modeled, explained, and by a model, but I'm not going to enter in this story. I just let you go to the paper. So if I summarize, the fast accumulation of sediments, of salt, inhibits the formation of an extrusive layer, and therefore inhibit the formation of high amplitude short wavelength magnetic anomalies. The observed low amplitude long wavelength anomalies are caused by deeper crustal sources. Again, and that has a consequence. That means that the continent-ocean boundary does not lie at the first clear magnetic anomaly, as it is often read in textbook, but it should be searched significantly landward, as shown in the Red Sea and the Gulf of Mexico examples. Conclusion of this part A, the observation from oceanic detachment, subduction zone, passive margins, ocean basin at satellite altitude, ocean basin from the detailed analysis of the anomaly shape, or ocean basin from the magnetic properties of rock samples, all those things support a significant contribution of the deeper crustal layers to the sea surface magnetic anomalies. And so, for example, the variable magnetic signature of oceanic complex mostly reflects the degree of magmatism at this segment. Strong anomaly on the detachment surface reflects the presence of exhumed gabbro bodies. And if the occurrence of these gabbro bodies is frequent, they record the sequence of polarity reversal and generate seafloor spreading anomalies. The loss of magnetization by alteration, by hydrothermal alteration before subduction, then the thermal demagnetization within the subduction suggests that titanomagnetite of the extrusive basalt contributes for 60% of the sea surface magnetic anomalies, the rest being caused by magnetite of the deeper crustal layers. And the removal by thermal demagnetization of the extrusive basalt contribution by post-accretion sedimentation at some passive margins, it absents due to the axial volcanic activity being smothered by syn-accretion sedimentation and salt flow at other margins, reveals the contribution of the deeper crustal layers to low amplitude, long wavelength magnetic anomalies. And the COB, continental ocean boundary, is not always at the first clear magnetic anomaly. Let's go now to a much smaller part B, where I try to explain the advantage to understand better the signal and the recorder to interpret the anomalies in complex basins. Well, the magmatic crust is not only recording the polarity reversals, as we read everywhere, but it is also able to record the geomagnetic intensity. And here you have two examples, one from the almost antipodal, one is from the EPR, East Pacific Rise, from our American colleagues. The other one is a work on the Central Indian Ridge. Both of them show that paleo intensity variations as recorded independently by sediments. It is this curve, lower curve here, and this is a yellow curve here. They are showing the same signal as the basalt, mostly the basalt observed from a deep toe measurements across the ridge axis on magmatic oceanic crust. So this is confirmed from observations within the Cretaceous normal superchrome, also known as the Cretaceous quiet zone. This area between about 80 million years here, where we have the first polarity the first polarity reversal of the recent sequence, and the older side at about 120 million year M0 for the Mesozoic series of anomalies. In between, there is no clear reversal. But you can see from this profile from the southwest Indian ridge, from the South Atlantic on the African or the American flank, you can see that the signal is pretty similar. Actually, what we see is that there is a lower variability at the beginning and at the end of the Cretaceous normal supercrown with a higher variability in the middle. And we see also that this marker Q1 and Q2 are robust and they can be recognized worldwide. So if we have markers, we can date the seafloor between 80 and 120 million years, which was shown impossible in the early reconstruction, as I was showing you on the slide on the animation, the small movie before. Okay, here is actually even a higher resolution signal. This is the Cretaceous supercrown seen on the surface, that is a ray profile, and on a deep toe profile. The deep toe here is in the Atlantic, the complete one, and the partial one only is from the Mozambique basins. And what we see, if we look a little bit closer, is that those signals that are collected at well, very far away from each other, at probably 10,000 kilometers away, they show more or less the same kind of signal. They show the same features, and that means that those features are definitely geomagnetic. So we have a lot of variation from this signal if we choose the correct, the nice magmatic crust that are showing up on the deep toe profiles. Now, how can we use that as a knowledge to better interpret our magnetic anomaly? Here is a place, one of the few places that remain quite unknown on the globe, where the magnetic anomalies were not clearly identified and recognized. And this is mostly the Columbia Basin and the Venezuela Basin within the Caribbean plate. There are places also with oceanic plateaus that I will not discuss. This is the magnetic anomalies. We see that the Columbia Basin is showing few anomalies here. These anomalies are on each side of what appear to be a fossil spreading center. And in the Venezuela Basin, we see on the gravities that we have a very strong anomaly here that correspond probably to a fracture zone, a fossil transform fault, and it shows up also on the magnetic map. So our interpretation, well, our interpretation is quite simple. We have a fossil spreading center here, and we have anomalies that are having small offset in this area. But what are those anomalies? Well, if we look at the profile, we see very clearly that this long area showing only small amplitude variation and no very clear, no very big anomaly is probably the Cretaceous quake zone. And so these two anomalies on each side of the fossil ridge are anomaly 34, 33 reverse and 33 in the middle at the axis. If we go to the Venezuela Basin, this smooth area is probably the youngest part of the Cretaceous normal supercrown, and the other anomalies that are fluctuating are probably the central part of the Cretaceous normal supercrown. And here is a comparison with the profile I was showing before. The Columbia Basin will be in this part, and the Venezuela Basin in this part. And that helps us to interpret the age of those basins and to reconstruct this evolution. And I encourage you to see the paper to see the continuation of the story that I cannot give here. Okay, so conclusion of this is the magmatic oceanic crust do not only record accurately the geomagnetic polarity reversal, but also the fluctuation of the paleointensity. And this should be used to identify anomaly in complex oceanic basins. There are several other examples, but I just showed one, which was the basins of the present-day Caribbean plate that was inferred for a long time to be Cretaceous from the rocks in the basin around. We confirmed this inference by identifying parts of the paleointensity signal observed on other good sea surface and deep toe magnetic anomaly records from other oceanic basins. And the last part, on the need to collect new, well-navigated magnetic data to increase the resolution of plate reconstruction. Well, you will never see a scientist that will tell you, I don't want new data, I am happy with what I have. Of course, we all want new data. But I want to point out that it is even worse than that. It is not adding a few good data to the existing good data. It is just replacing many of the old data that are not good enough for the task. Those are the magnetic anomaly data available from the World Digital Magnetic Anomaly Map 2.0, and you can see that those data are strongly uneven. There are places where we have excellent coverage, like around Japan and in the Western Pacific. We have the North Atlantic ridge is pretty well surveyed. Around Norway is very well surveyed. In the Arctic, there are aeromagnetic data. In the Pacific, along California, near Hawaii, near Australia, New Zealand. Yes, those areas are well covered. But there are many areas where we have very sparse data, like the South Pacific, the Southern Indian Ocean, the South Atlantic, and the Central Indian Ocean as well. And we have seen that in areas like the Gulf of Mexico and the Caribbean plate, even we have quite a lot of data, it's quite difficult to read those data. Those data, in many of those remote areas, they predate modern satellite navigation. And then the navigation is okay within a few kilometers, sometimes more than that. Our knowledge on plate motion, on the past plate motion, strongly rely on these old data. And new magnetic profiles may lead to important revisions and major discoveries, particularly in the past plate motion of small amplitude. There are quite a lot of motion that are not seen because they are below the uncertainty of the present data. We are showing in the next slide that two short profiles representing each only an additional day on the transit to Antarctica. They added 17 million years of existence to a plate boundary. And this is a work conducted with Roy Granot. Those are the plates. The plate today are Australian, Pacific, and Antarctica. But in the past, there were two Antarcticas. There were East Antarctica, that surprisingly, because it is seen from the American side, is on the left, and West Antarctica, that is on the right. Yes, the Earth is a sphere, remember. Okay, there is also complication with the Macquarie plate, but I'm not going to discuss this complication. I recommend you to read the paper if you are interested. And we took advantage of the icebreaker L'Astrolabe to go to Dumont d'Urville French Antarctic Station to collect new data. And these are the data we collected. Those are the, well, here is the ridge, the Southwest Indian Ridge. The area where Korean scientists goes often is in this area. Further in this area is the Indian Ocean. So we started from Hobart and went down to the ice before going to the polar station. And we did that twice because strong constraints from the ice condition in 2012, 2016. And you can see that the data are of excellent quality. And well, if you use this data to constrain the motion of the different plates, this data constrain very well and are in total agreement with data located further west, and they reflect the motion between Australia and East Antarctica. Conversely, if you reconstruct those data, you can see that until 10 million years, that is these two anomalies here, they are consistent with what is observed further east. So that means at that time, there were only one Antarctic plate. But if you go beyond that, between these 11 million years and something like 28 million years when there were recognized motion on the Antarctic basin between East and West Antarctica, you can see that the anomalies here, anomaly 6 and anomaly 5C, they show a discrepancy on this side, where, on this side, yes, where there is no discrepancy on the other side. And it just means that what was supposed to be a motion until 28 million years should be extended to actually a motion until 11 million years. This reflects actually the fact that we are still having motion between Australia and West Antarctica, which that is different from the motion between Australia and East Antarctica. And this records actually the motion between East and West Antarctica. This structure here, next to the Baleine Islands, is probably related to an ultra-slow spreading center that was previously unrecognized, and that should be explored for confirmation. So adding 17 million years of existence for plate boundary is not a small thing. This has consequences. The motion of East and West Antarctica has consequences of a lot of reconstruction, because this is the only plate circuit that allow us to connect Pacific plates to the other plates. So it is of tremendous importance. And this is just a small example showing you how adding 2 days of data collection can really change our understanding. So here is a poll, the stage poll before 28 million years and after. So we can see there were significant change, as much as we can say with the limited data set that we have. And this is the plate boundary here in the Baleine Island, as I was telling you, in the Adare Basin, Terror Rift, and in the Ross Sea. Okay, so my conclusion for this area is that we should collect data. I'm not repeating that, but the second order motion is really very important. And I think we should really put some effort on that, because first, it costs nothing to tow a magnetometer, or very little to tow a magnetometer, even when it is not at the core of the research proposal for the cruise that is ongoing. And I think by doing so, we should progressively go to something that we could call Plate Tectonics 2.0. We have the 1.0. We understand well the motion between the main plates, but there are still a lot of uncertainty. For instance, there are plates that are inferred and that are not confirmed, like the Vandal plate between the Somali plate and the Nubia plate close to the Southwest Indian Ridge. It may rely on a bad interpretation of some magnetic anomaly or not. There are discussions. Well, having good, well-navigated new magnetic profile would help to solve those problems and understand better the small amplitude motions at the surface of the Earth. My final conclusion, well, despite the variety of topics in this talk, I could have spoken much more about our various deep flow experiments to better constrain the geomagnetic field past history, about our various deep sea submersible, ROV, AUV experiment to investigate volcanism and hydrothermalism, and about the plate tectonic evolution of various ocean basins. I focused on what the study of various plate tectonic features tell us about the magnetic structure and properties of the oceanic lithosphere from birth to disappearance. That was my part A. And there is now little doubt that the deep crust, most probably gabbro, and in some cases, serpentinized peridotite, is a significant source of the anomalies. In the first short addition, the part B, I wanted to show how different aspects of the solution are interacting to progress. Without a study on the geomagnetic fluctuation within the Cretaceous normal supercroon, no identification of anomalies on the Caribbean plates. And there are many examples similar to that, where a study you do on one thing is actually giving you the solution on another problem. In the second short addition and part C, I wanted to insist on the weakness of the database on which quantitative plate reconstruction rely. It is still essential to acquire marine magnetics. As I said at the beginning, it is cheap, it is easy, and I hope I could convince you that it brings great results. Thank you for your attention.